Hello everyone and welcome to this tutorial on using Excel solver for a common fluid mechanics design problem, pipe diameter sizing. Today we'll learn how to determine the required pipe diameter to meet specific flow rate and pressure drop requirement. So here is the problem statement. Let's quickly recap our problem. So we need to design a pipeline to transport water at 20 degrees centigrade. The pipeline is 5 meter long and made of commercial steel, must transport to a volumetric flow rate 0.05 cubic meter per second. And then maximum allowable pressure drop over this length is 150, means 1,50,000 pascals, means 150 kilopascal, to minimize pumping cost. Now our goal is determine the minimum required internal diameter of the pipe. So here are the given datas. Pipe length, that is 500 meters, volumetric flow rate Q, that is 0.05 cubic meter per second, absolute roughness epsilon for commercial steel, that is 0.000045 meter, which is 0.045 millimeters. Maximum allowable pressure drop delta P max, that is 150 kilopascal. Fluid properties: water at 20 degrees Celsius, density rho, that is 998.2 kg per cubic meter, and dynamic viscosity mu 0.001002 pascal second or kilogram per. To solve this problem, we need some formula. So here are the theoretical background. So first is that Darcy-Weisbach equation, means head loss to pressure drop. So that del P is equal to FL by D rho V square by 2. So here del P is the pressure drop, Pascal or Newton per meter square. F is the Darcy friction factor, dimensionless. L is the pipe length. Then D is the pipe inner diameter. Rho is the fluid density and V is the average fluid velocity. So then 2 is volumetric flow rate Q and velocity V. So here we are given Q and need to find D. So we express V in terms of Q and D. So V is nothing but Q by cross A cross section, means Q by cross sectional area. So we can write 4Q pi D square. Now Reynolds number, we know that rho V d by mu. So substituting this expression V, so Re is nothing but rho V d by mu. So here that V is 4Q by pi d square into D by mu, or we can write rho V d by mu. So here mu is the dynamic viscosity, and we know the relative roughness epsilon by D. So the absolute roughness epsilon is the pipe property, but the relative roughness depends on the unknown diameter D. And here, so we need to calculate the F, as here from here we have to calculate the pressure drop. So for that we need this equation. So 1 by root F is equal to minus 2 log 10 epsilon by D 3.7 plus 2.51 Re root F. So this theoretical background we have to solve this. Before going to solve by using Excel solver, so we have set up all these parameter and its values. So in this column, so we have written all this parameter what we need for solving this problem, and this column we will put to the values, also calculate some values, and here is this column will put some description. So first parameter is L. L is nothing but 500, so that is pipe length in meter. The Q is given, so that is 0.05 volumetric flow rate meter cube per second. Epsilon, that is also given, so that is absolute roughness in meter, that is 0.4045. Delta P max also given in the problem, so that is 150 kilopascal or 1,50,000 pascal. Then rho for water at 20 degrees Celsius, that is also given, means we have to assume that, so that is I'm taking 998.2 fluid density. And viscosity we have to take that, so viscosity I am taking here that 0.001002 dynamic viscosity. And pi For calculation area, so we need to take that pi. So pi we already know that 3.14, that constant, and here I am taking the guess value, so that will change when that solver solve the problem. So this is the initial guess value, pipe diameter 0.1, solver change this, and initial guess value for friction factor, solver changes this. Now we have to calculate v, velocity. So how do you calculate velocity? Because here that volumetric flow rate is given, so we can calculate v is nothing but q by a. So from here, by using that equation, we can solve this problem. So for that, we have to set up this equation. So here I am putting different color. So calculate the velocity from q given by q given, and d actually we are taking the guess value. So the velocity will be, that is 4q, 4 into q is here 0.05 divided by pi. So we are taking the bracket, so pi is here into d square, d guess value is 0.01, that's square. So that we have calculated the velocity. So velocity is 6.36942672. Then we have to calculate Re. Re we know that is rho dV by mu. So that we can easily calculate. That is equal to rho. Rho is here. Rho into V. V is here. Into D. D is the guess value. Divided by mu. Mu is here. So you got that calculated Reynolds number. Then we have to calculate epsilon by D. So epsilon by D we have to calculate. So epsilon by D is, epsilon is here divided by D. D is the guess value. Then we have to calculate. So now this is the Colebrook equation, left hand side and right hand side. So left hand side is something like, so you have to calculate that left hand side and right hand side. So left hand side is 1 by root f. So that is 1 divided by SQRT of that f guess value. So here is the f guess value. So that we got. Then RHS. RHS is minus 2 log 10. So minus 2 into log base 10. Then epsilon by D already we have calculated, divided by 3.7 plus then 2.51 divided by RE. RE is already we have calculated, RE is here, into SQRT root of F. F is here, this is here, and then we have to put another bracket, that's it. So we got the result, that RH Colebrook equation. Then we have to calculate delta P. Delta P is something like, delta P we have to calculate. So that is nothing but F of, that is F is here, F into L by D. So L is already we know that 500 divided by D. D is the guess value, L by D. Then multiply rho is here, into V square. V square is V square by 2. So we put the bracket on the whole term and then divided by 2. So we'll got that delta P calculation. Now here is the objective function. Objective function means, so here that LH minus RH means, if I take this term LH and RH in that right hand side, so that will be 0. So here I am doing LH minus RHS. So that will be my objective function, and our target to 0. So here we are doing that LH minus RHS. So solver will change this value and it will make 0. Then delta P, so this is not the objective function, we don't need that. Then delta P residual. So here, so we have already calculated delta P. So that calculated delta P is here minus that given delta P max is this. So that is something. Now we'll use Excel solver. So if you don't find that Excel solver, so you will go, so here option and then add-ins, then go, then here you have to tick mark and then OK. So that will come in the data and here that solver. Now I am using that solver. So here my objective function is this cell, so that will be 0 by changing the D and F. So for that I am selecting that 2 cell. Okay, and then constant is that the D value must be greater than 0. I am putting some 0.01 add, and F value that must be greater than something, greater than obviously 0. So this value greater than equal to, I'm putting 0.00001 small value I'm putting. Another is here, so delta P residual must be 0. So for that I'm selecting this one, that is equal to 0. Now OK. Now here, so I have to tick mark, make unconstant variable non-negative, and here I am using GRG non-linear, that is the method. Okay, now if I solve, I'll get some result. Now answer OK, so that will give the solution. So now here you can see that Colebrook residual is, that is nearly 0, delta P residual is also 0, and that delta P calculation, that is 1,50,000 nearly. Okay, and everything is set. Right, now here our D gauge value is this, means this is actually the pipe diameter and the friction factor. So D means friction factor, and I can write here, so D is nothing but 0.161769971. I can take that, and friction factor is something 0.01641435. So that is our solution. Now you got the result. So D is 0.161769971 and friction factor 0.01641,435. So in this problem, so goal is determine the minimum required internal diameter of the pipe, so that is 0.161769971. So now congratulations, so you have now successfully used Excel solver to perform a complex pipe diameter sizing calculation and demonstrating its power in solving coupled nonlinear equation. This method is invaluable for many engineering design problems. So thank you for watching. If you like this video, please hit the subscribe button. Thank you once again.